Hello to everyone. Now I am going to explain about the physics involved in food processing. On that we are going to know about physics involved in coffee. The coffee is slightly less dense than the milk, so it has a tendency to float on top. If it is poured quickly enough, however, it will penetrate more deeply into the milk and the two liquids will form a turbulent and chaotic mixture. Now, as the mixture begins to cool down, double diffusion convection comes into play. If you pour coffee into warm milk at just the right speed, the law of physics will make the two liquids arrange themselves into an elegant series of layers shading from white to dark brown. According to a new study that may have applications far beyond the barista's realm. The secret Howard Stone of Princeton University, US, and colleagues write in Nature Communications lies in a phenomenon known as double diffusion convection, which occurs when variations in density and temperature work together to create self-sustaining loops of flowing liquids. Double diffusion convection. Double diffusion convection is a fluid dynamics phenomenon that describes a form of convection driven by two different density gradients which have different rate of diffusion. Convection in fluid is driven by density variations within them under the influence of gravity. These density variations may be caused by gradients in the composition of the fluid or by absence of difference in temperature through thermal expansion. Thermal and composition gradients can often diffuse with time, reducing their ability to drive the convection and requiring that gradients in other regions of the flow exist in order for convection to continue. Two quite different types of fluid motion exist and therefore are classified accordingly depending on whether the stable stratification is provided by the density affecting component with the lowest or the highest molecular diffusivity. These are all the pictures that depicts about double diffusion convection. On the left side we are seeing a coffee depicts a double diffusion convection theory. On the right side it is the pH of this theory. Physics in size of coffee. According to nanotechnology scientist David, the size of coffee grains has a big impact. Larger coarse particles are more permeable, which means the hot water flows more quickly through them. And if the water flows too quickly, you are likely to get an under extracted coffee. By contrast, smaller particles hold the water in amongst themselves and slow its flow. But when these fine grains are steeped in water for too long, more of the bitter caffeine flavor seeps out, resulting in an over extracted coffee. To demonstrate to coffee appreciators the impact of grain size on flavor, David uses a simple experiment. He extracts coffee from different grains into a separate beakers. Then, using a machine called a reflexometer, he measures how many dissolved solids have been extracted from the coffee. Heat transfer in coffee roasting. During roasting, heat is transferred to coffee bean in the roaster by conduction, convection, and radiation. In drum roasters, 70% of heat is transferred by convection and 30% by conduction. Heat transfer by conduction, convection, and radiation. Coffee roasters' inner temperature must reach to a certain temperature level, which is preferably over 180 degrees Celsius before roasting. After beans are loaded, interior temperature level starts to drop. Most of the primary heat transfer is by convection. Hot coffee beans transferring their own heat to other beans by reflection is the heat transfer by convection. Heat source has no direct contact with drum in hot air drum roasters. Hot air is generated in a separate heater and heats the bean as it flows through. Surface temperature of the drum is low during roasting. In hot air roasters, most of the heat is transferred by convection. Temperature, mass transfer, and moisture. At least the first 2 by 3 of roasting process is endothermic. Beans absorb energy and heat moves from outside to inside the beans. Delta value is at top level in fast roasting while lower in slow roasting. Experts measurement results indicates that interior pressure varying from 5 to 4 atom to 25 atom increases enough to rupture bean cellulose matrix, and then first pop occurs. Central heat of the bean decreases while pressurized water vapor and CO2 gas escapes from the crack. During roasting, moisture inside the drum as well as the bean affect the heat transfer. After the first delay, moisture inside the drum increases the effect of heat transfer and accelerate moisture loss inside the bean. However, bean's inner moisture has more complicated effects during roasting. These are all the applications of physics involved in make food processing in coffee.